video will cover source transformation. So this is a technique for simplifying complicated circuits. So here we identify parts of the circuit that contains a voltage source in series with the resistance and convert that into a current source, or a current source that is in parallel with the resistance and convert it into a voltage source. Let's say I have a voltage source that is in series with the resistance. According to source transformation, this configuration can be converted into a current source that is in parallel with the resistance, where this current source is equals to E divided by R, and the resistance where that source is parallel is equals to R. So this R here is simply a copy of this R here. The direction of the current source is towards A because the plus sign here is facing the terminal A. In the same manner, if we have a current source that is in parallel with the resistance, that configuration can be converted into a voltage source that is in series with a resistance, where the voltage is equals to IR, and this resistance is also equals to R. So this one is simply a copy of this one. Take note that the plus sign of the voltage source is facing terminal A because the current here is pointed to terminal A. Source transformation is really just a consequence of the relationship between Thevenin's theorem and the Norton's theorem. So let's see what this means. So let's say I have a source that is in series with a resistance, and I'll convert this into a Norton's equivalent. So that means that I need a current source that is in parallel with a resistance. So this one is I sub n, and this one is R sub n. To get R sub n, we look into the open terminals and get the open circuit resistance. And since we only see an independent source, we can use case 1 to determine that resistance. So the rule is to disable the source. Since it is a voltage, we short out the terminals. So what we get there is a resistance that is actually equals to R. So that means that this one is equals to R. To get I sub n, we short the open terminals and determine the current that flows from terminal A to terminal B, and we designate that as our I sub SC. Clearly, I sub SC is equals to E over R, and I sub n becomes ISC, which is E over R. Similarly, let's say we want to convert this circuit. So this is a current source that is in parallel with the resistance into its Thevenin's equivalent. So that means we're looking for voltage source VTH that is in series with a resistance. where the resistance is RTH. To get RTH, we look into the open terminals, and since we find an independent current source, we disable that by opening the source. So that means what we get here is equals to R, and our RTH becomes R. For VTH, we compute for voltage across the open terminals, and we designate that as our VOC. And clearly, this current will simply flow towards the resistance. So that means the voltage across here will be VOC, and that would be equals to I times R. So our VTH becomes our VOC, which is IR. Let us take this example to illustrate source transformation. This is the same example that we have in Thevenin's theorem. The role of source transformation is to simplify complicated circuits. That means we reduce the number of loops into a sufficiently small number, preferably a single loop, from where we can solve the parameters easily. To reduce this, we look for parts of the circuit that is a current source that is in parallel with a resistance, or a voltage source that is in series with the resistance. Here, for example, you see that here we have a 4 ampere source that is in parallel with a 3 ohm resistance, and also a 2 ampere source that is in parallel with a 5 ohm resistance. So both of these can be converted into a voltage source. So let's do that. So for the 4 amperes, so we have here a current source in parallel with the resistance, which is 3 ohms. This is 4 amperes. So take note that this point here is really this point here also, and this point here is also this one. So we could convert that into a voltage source that is in series with the resistance. The resistance here is copied from the original configuration. Now, where is the plus sign of the voltage source? Since this current 4 amperes is directed to this point, that means the plus sign should be here. So this is the minus sign, and the magnitude will be 4 times 3, so that will give us 12 volts. Okay, so this is the converted uh, portion. So for this one, so we have a resistance in parallel with the current source. So this is 5 ohms. This is 2 amperes. So that can be converted into a voltage source in series with a resistance. Now this point here is this point. So that's why the plus sign is at the top, because the 2 amperes is directed to this point. So this is 2 times 5, so this is 10 volts, and we copy the 5 ohms. Okay. Then we replace the part with the equivalent circuit, and that should give us this circuit. So this is our 12. So this would be, so here this is 10 ohms. Okay, so this is our voltage that is in series with the resistance, and this is the 2 ohms, and then okay, so this one is 12 volts, 3 ohms, this is 2 ohms, this is 10 volts, this is 5 ohms, and 4 ohms, and this is a high knot. Okay, so that is the simplified circuit. So this is 10 ohms here. Uh, Take note that this, and this are now all in series. So we could actually add the resistances and the two voltages that are in series. This is our simplified circuit. So we brought down the number of loops from 4, and now it's just 2 loops. Notice that we did not touch this portion, so it's a voltage source in series with a resistance, because this will affect our parameter I sub naught. Okay, so notice that we have here several elements that are in series. So for example, 12 volts and 10 volts are in series, although they are not near each other, they are considered series. Okay, so we can, so this is our 12 volts. We can actually transfer the 10 volts near the 12 volts, and you will notice that they are in series. Okay, so plus, minus, plus, minus, they are not only in series, they're also additive. So if we combine this will become 22 volts. Also, the 3 ohms, 2 ohms, and 5 ohms are also in series, and we can combine those into a 10 ohm resistor. So therefore, that will give us an even more simpler circuit that looks like this. Now we have a voltage source that is in series with a 10 ohm resistance. And that means that I can redraw the circuit into something like this. So this is my 12 volts. So I have your resistance. So that thing, the 22 volts and 10 ohms, can be converted into a current source, an independent current source, and parallel resistance. So this one is 10 ohms. Okay, and current source should be 22 divided by 10, so that will give us 2.2 amperes. So this is 10 ohms here, and this is 4 ohms. So this is our I naught. Okay. Um, we added one loop, but the purpose here is for us to be able to combine the resistances. So notice that these 10 ohms here and 10 ohms there are in parallel because they are connected to the same uh, node. So node there and node here. Okay, so that means I can combine the two 10 ohm resistances, and since they are in parallel, that makes it a 5 ohm resistance. So therefore, I can further reduce the circuit or redraw the circuit into something like this. Okay, so like that. So this is 4 ohms, this is 5 ohms, and this is 2.2 amperes. Okay, so this is our I naught, and here is 12 volts. Now we have a resistance in parallel with a current source, so therefore we can again convert that into a voltage source. So that will give us something like this. So this is 4 ohms, this is 5 ohms, and the voltage source is 2.2 times 5, that is 11 volts. Okay, so this is I naught here. Take note that I naught will now flow throughout the single loop. So we're able to reduce the original circuit into a single loop without uh, affecting the parameter I naught. So that will bring us to this very simple circuit, a single loop circuit, from where we can write our KVL. Okay. So again, as I've said, I naught will now flow around the loop. So this is I naught. So we can write KVL from this loop. So that's minus 12 uh, plus, so 4 plus 5, we have 9, I naught plus 11 equals 0. And we can compute I naught as equals 1 over 9 amperes, which is our answer also when we solve this using Thevenin's theorem. I must emphasize that in solving complicated circuits, we could actually combine the tools that we've already learned. So for example, we can reduce this using source transformation. We can convert this into a Thevenin's equivalent circuit. So it's sometimes faster to do that, and it could save you steps. Thank you.